NEC 110.10 mandates that electrical systems must be safeguarded against overcurrent conditions, including short circuits and ground faults, to avert fire hazards and equipment damage. The fault current ratings of insulated wires typically stem from short circuit currents capable of inflicting immediate damage to the insulation, potentially leading to fires. These ratings generally fall below the interrupting ratings of circuit breakers. Circuit breakers are engineered to interrupt fault currents within a specific time frame. The open time, or clearing time, of a circuit breaker signifies the duration required for the breaker to trip and halt the flow of current, with a shorter open time indicating a swifter response. UL 489 serves as a safety standard for molded case circuit breakers. Circuit breakers bearing the UL 489 listing undergo testing to ensure their ability to safely interrupt fault currents within their designated interrupting ratings. Consider a scenario where an electrical inspector raises concerns about the adequacy of protection for number 12 wire against fault currents despite the circuit breaker's UL 489 listing and a 20 amps interrupting rating. This concern arises from the availability of a 40 kA fault current at the panel, significantly exceeding the wire's fault current rating of 2768 amps. Industry practice typically deems number 12 wire adequately protected by a 20 amp circuit breaker in a panel with a fault current of 40 kA or less, assuming the circuit breaker interrupts the fault current rapidly enough to prevent wire damage. However, should the electrical inspector insist on additional protection, several options may be considered. Firstly, installing a circuit breaker with a lower interrupting rating such as 10 amps or 15 amps. Secondly, using a larger wire size such as number 10 or number 8. Thirdly, installing a ground fault circuit interrupter, GFCI, or arc fault circuit interrupter, AFCI, in conjunction with a circuit breaker. The matter at hand involves code interpretation and industry practice. While the electrical inspector's concern holds validity, it does not represent the sole means of complying with NEC 110.10. Engaging in further discussion with the inspector to reach a mutually acceptable solution may prove beneficial. Fault current protection in electrical systems is a critical aspect of safety and code compliance. When evaluating the adequacy of wire protection against fault currents, it's essential to consider several factors, including the available fault current at the source, the interrupting rating of the circuit breaker, and the fault current rating of the wire itself. NEC 110.10 emphasizes the need to protect electrical systems from overcurrents, including short circuits and ground faults. Overcurrents can lead to insulation damage, conductor melting, and potentially fires, posing significant safety risks. The fault current rating of a wire indicates the amount of current the wire can withstand for a short period, typically one cycle, without sustaining damage. These ratings are generally lower than the interrupting ratings of circuit breakers, as they represent the wire's ability to withstand a fault condition until the breaker trips. Circuit breakers are designed to interrupt fault currents within a specified time frame, known as the clearing time or opening time. This time is critical in limiting the amount of energy that flows through the circuit during a fault, thereby minimizing potential damage. UL 489 is a widely recognized safety standard for molded case circuit breakers. Circuit breakers listed under UL 489 undergo rigorous testing to ensure their ability to safely interrupt fault currents up to their rated interrupting capacity. This testing includes verification of the breaker's ability to trip quickly and reliably under various fault conditions. In practical applications, electrical inspectors often assess the adequacy of wire protection based on industry practices and code interpretations. While a 20 amp circuit breaker is commonly considered sufficient for protecting number 12 wire in a panel with a fault current of 40 kA or less, inspectors may raise concerns if they believe the wire's fault current rating is exceeded. This concern is valid, as the available fault current at the panel can significantly exceed the wire's short time withstand rating. To address such concerns and ensure compliance with NEC 110.10, several options can be considered. Firstly, installing a circuit breaker with a lower interrupting rating such as 10 amps or 15 amps can limit the amount of fault current that flows through the wire during a fault. However, this approach may also reduce the circuit's capacity to handle normal load currents. Secondly, using a larger wire size, such as number 10 or number 8, can increase the wire's fault current rating, providing a greater margin of safety. However, this approach may require replacing existing wiring and could be more costly. Thirdly, installing a ground fault circuit interrupter, GFCI, or arc fault circuit interrupter, FSI, in addition to the circuit breaker, can provide additional protection against ground faults and arc faults, respectively. GFCIs and FSIs are designed to detect and interrupt these types of faults quickly, further reducing the risk of damage. In conclusion, ensuring adequate wire protection against fault currents involves a comprehensive assessment of the electrical system, including the available fault current, the interrupting rating of the circuit breaker, and the fault current rating of the wire. While industry practices and code interpretations provide guidance, it's essential to address any concerns raised by electrical inspectors and implement appropriate measures to comply with NEC 110.10. By considering the various options available and working collaboratively with inspectors, you can ensure the safety and reliability of electrical systems. When dealing with electrical installations and inspections, understanding the relevant codes and standards is crucial. NEC 110.10, which pertains to the protection of electrical systems from overcurrent conditions, is one such standard. This standard aims to prevent fire hazards and equipment damage by ensuring that electrical systems can safely handle short circuits and ground faults. One of the key considerations in complying with NEC 110.10 is the fault current rating of insulated wires. This rating indicates the amount of current a wire can withstand for a short period, typically one cycle, without sustaining damage. It's important to note that the fault current rating of a wire is generally lower than the interrupting rating of a circuit breaker. Circuit breakers are designed to interrupt fault currents within a specified time frame. This interruption time, also known as the clearing time or opening time, is critical in limiting the amount of energy that flows through the circuit during a fault. A shorter interruption time means less energy is allowed to flow, reducing the risk of damage to the wire and other components. UL 489 is a widely recognized safety standard for molded K circuit breakers. Circuit breakers listed under UL 489 undergo rigorous testing to ensure their ability to safely interrupt fault currents up to their rated interrupting capacity. This testing includes verifying the breaker's ability to trip quickly and reliably under various fault conditions. When an electrical inspector raises concerns about the adequacy of wire protection, it's essential to address those concerns and ensure compliance with NEC 110.10. In the case of number 12 wire protected by a 20 amp circuit breaker in a panel with a 40 kA fault current, the inspector may be concerned that the wire's fault current rating is exceeded. While industry practice often considers this configuration acceptable, the inspector's concern is valid, as the available fault current at the panel can indeed exceed the wire's short time withstand rating. To address this concern and ensure compliance with NEC 110.10, several options can be considered. Firstly, installing a circuit breaker with a lower interrupting rating, such as 10 amps or 15 amps, can limit the amount of fault current that flows through the wire during a fault. However, this approach may also reduce the circuit's capacity to handle normal load currents. Secondly, using a larger wire size, such as number 10 or number 8, can increase the wire's fault current rating, providing a greater margin of safety. However, this approach may require replacing existing wiring and could be more costly. Thirdly, installing a ground fault circuit interrupter, GFCI, or arc fault circuit interrupter, FSI, in addition to the circuit breaker, can provide additional protection against ground faults and arc faults, respectively. GFCIs and FSIs are designed to detect and interrupt these types of faults quickly, further reducing the risk of damage. When evaluating these options, it's important to consider the specific requirements of the installation and the potential impact on circuit performance. Consulting with a qualified electrical engineer or electrician can help determine the most appropriate solution for a given situation. Ultimately, the goal is to ensure that the electrical system is protected against overcurrent conditions in accordance with NEC 110.10, preventing fire hazards and equipment damage. By carefully considering the fault current rating of wires, the interrupting rating of circuit breakers, and the availability of additional protective devices, you can create a safe and reliable electrical installation. Remember that electrical codes and standards are subject to change, so it's essential to stay up to date on the latest requirements. Consulting with a qualified professional and adhering to industry best practices can help ensure that your electrical installations are safe, compliant, and reliable. The National Electrical Code, NEC Section 110.10 is a cornerstone of electrical safety, dictating that electrical equipment must be protected against damage from overcurrents, including short circuits and ground faults. The goal is to minimize the risk of fire, explosion, and other hazards that can arise from electrical faults. Understanding this requirement involves considering several key factors. Firstly, available fault current. Secondly, interrupting rating of protective devices. Thirdly, conductor withstand ratings. Available fault current refers to the maximum current that an electrical system can deliver during a short circuit or ground fault. This value is determined by the characteristics of the power source, such as a transformer or generator, and the impedance of the circuit. The higher the available fault current, the greater the potential for damage to equipment and conductors. Interrupting rating is the maximum fault current that a protective device, such as a circuit breaker or fuse, can safely interrupt without failing. Protective devices must have an interrupting rating equal to or greater than the available fault current at their point of installation. Conductor withstand ratings indicate the amount of fault current that a conductor can withstand for a specific duration without sustaining damage. These ratings are typically expressed in terms of amps squared seconds, which represents the amount of energy that the conductor can absorb before its insulation melts or its mechanical integrity is compromised. In the situation presented, the concern revolves around whether a number 12 wire is adequately protected by a 20 amp circuit breaker in a system with a 40 kA available fault current. The electrical inspector's concern stems from the fact that the number 12 wire has a limited withstand rating, and the 40 kA fault current could potentially damage the wire before the 20 amp circuit breaker has time to trip. While a 20 amp circuit breaker is designed to protect the number 12 wire from overload conditions, it may not be sufficient to protect it from high magnitude fault current. To address this concern, several options can be considered. Firstly, current limiting circuit breakers. Secondly, series rated systems. Thirdly, current limiting fuses. Fourthly, conductor upgrades. Fifthly, engineering studies. Current limiting circuit breakers are designed to rapidly reduce the magnitude of fault currents, limiting the amount of energy that flows through the circuit. These breakers have a much faster response time than standard circuit breakers and can significantly reduce the risk of conductor damage. Series-rated systems involve coordinating the interrupting ratings of multiple protective devices in a circuit. By using a combination of circuit breakers with different interrupting ratings, it is possible to achieve adequate fault current protection without having to replace all of the existing circuit breakers. Current limiting fuses are another option for limiting fault currents. These fuses are designed to melt very quickly when subjected to high currents, interrupting the fault before significant damage can occur. Upgrading the conductor size can increase its withstand rating, making it more resistant to damage from fault currents. However, this option can be expensive and may not be feasible in all situations. Performing an engineering study can help to determine the actual fault current levels at various points in the electrical system. This information can then be used to select the appropriate protective devices and ensure that the system is adequately protected. It is important to note that the NEC requires that electrical systems be designed and installed in accordance with accepted engineering practices. This means that a qualified electrical engineer should be involved in the design of any electrical system where high fault currents are present. In conclusion, ensuring adequate fault current protection is essential for electrical safety. By carefully considering the available fault current, the interrupting ratings of protective devices, and the conductor withstand ratings, it is possible to design and install electrical systems that are protected from the hazards of overcurrents. Consulting with a qualified electrical engineer is recommended to ensure that all applicable codes and standards are met. In electrical engineering, protecting electrical systems from fault currents is a paramount concern. Fault currents, which are abnormally high currents that flow during short circuits or ground faults, can cause significant damage to equipment, conductors, and even pose a safety risk to personnel. NEC 110.10 mandates that electrical equipment be protected against damage from overcurrents, including fault currents. This requirement necessitates a thorough understanding of fault current calculations, protective device coordination, and conductor withstand ratings. To ensure adequate fault current protection, engineers employ a variety of techniques and devices. Firstly, fault current calculation. Secondly, protective device coordination. Thirdly, conductor selection. Fourthly, current limiting devices. Fifthly, ground fault protection. Fault current calculations are essential for determining the magnitude of fault currents that can occur at various points in the electrical system. These calculations take into account the characteristics of the power source, such as transformers and generators, as well as the impedance of the circuit. Protective device coordination involves selecting and coordinating the interrupting ratings of protective devices, such as circuit breakers and fuses, to ensure that they can safely interrupt fault currents without causing damage to equipment or conductors. Conductor selection plays a crucial role in fault current protection. Conductors must be sized to withstand the fault current for the duration of the fault without exceeding their temperature rating or suffering mechanical damage. Current limiting devices, such as current limiting circuit breakers and fuses, are designed to rapidly reduce the magnitude of fault currents, limiting the amount of energy that flows through the circuit. Ground fault protection is another important aspect of fault current protection. Ground fault protective devices, such as ground fault circuit interrupters, GFCIs, and ground fault relays, are designed to detect and interrupt ground faults, which can pose a significant safety risk. In the specific scenario involving the number 12 wire protected by a 20 amp circuit breaker in a system with a 40 kA available fault current, the electrical inspector's concern is valid. The number 12 wire has a limited withstand rating, and the 40 kA fault current could potentially damage the wire before the 20 amp circuit breaker has time to trip. To address this concern, several options can be considered, as previously mentioned. In addition to these options, it is also important to ensure that the electrical system is properly grounded. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to reduce the voltage rise on equipment and conductors during a fault. Furthermore, it is essential to conduct regular inspections and maintenance of electrical equipment to identify and correct any potential problems before they can lead to a fault. This includes inspecting circuit breakers, fuses, conductors, and other components for signs of wear, damage, or overheating. In conclusion, fault current protection is a critical aspect of electrical safety. By understanding the principles of fault current calculations, protective device coordination, and conductor withstand ratings, engineers can design and install electrical systems that are protected from the hazards of overcurrents. Consulting with a qualified electrical engineer is recommended to ensure that all applicable codes and standards are met and that the electrical system is properly protected. The scenario presented highlights a common challenge in electrical installations: ensuring adequate protection against fault currents. The electrical inspector's concern regarding the number 12 wire and its protection by a 20 amp circuit breaker in a 480 volts panel with a 40 kA fault current availability is rooted in the potential for the wire to be damaged before the circuit breaker can effectively trip and interrupt the fault. To delve deeper into this issue, let's explore some key concepts. Firstly, fault current availability. Secondly, conductor withstand capacity. Thirdly, protective device characteristics. Fourthly, code compliance. Fault current availability is the maximum amount of current that a system can deliver during a short circuit condition. It's determined by the upstream power source impedance, such as the utility transformer, and the impedance of the circuit up to the point of the fault. Higher fault current availability means a greater potential for damage if a fault occurs. Conductor withstand capacity refers to the ability of a conductor, in this case the number 12 wire, to withstand the heat generated by a fault current for a specific duration without failing. This capacity depends on the conductor material, insulation type, and size. Protective device characteristics encompass the tripping characteristics and the interrupting rating of the circuit breaker. The circuit breaker must be able to trip quickly enough to limit the energy let through to the conductor and have an interrupting rating sufficient to safely interrupt the available fault current. Code compliance revolves around meeting the requirements of the NEC, specifically Section 110.10, which mandates that electrical equipment be protected against damage from overcurrents, including fault currents. Now let's analyze the situation. The number 12 wire has a specific ampacity rating, typically 20 amps for general use, as well as a withstand capacity against fault currents. The electrical inspector's concern is that the 40 kA fault current availability significantly exceeds the withstand capacity of the number 12 wire. Even though the 20 amp circuit breaker is designed to trip and protect the wire from overloads, it may not react quickly enough to prevent damage during a high magnitude fault. This is because the circuit breaker's interrupting rating is the maximum fault current it can safely interrupt, but the energy let through during the tripping process can still damage the wire. To address this concern and ensure compliance with the NEC, several strategies can be employed. Firstly, current limiting circuit breakers. Secondly, series ratings. Thirdly, conductor upgrades. Fourthly, supplemental protection. Fifthly, engineering assessment. Current limiting circuit breakers are designed to rapidly reduce the magnitude of fault currents, limiting the amount of energy that flows through the circuit. They achieve this by using special designs that create a high impedance during a fault, quickly reducing the current. Series ratings involve coordinating multiple circuit breakers in series to achieve a higher overall interrupting rating. This requires careful coordination to ensure that the upstream breaker trips before the downstream breaker, limiting the fault current at a level that the downstream breaker can safely interrupt. Conductor upgrades involve replacing the number 12 wire with a larger conductor size such as number 10 or number 8, which has a higher withstand capacity against fault currents. This approach increases the system's ability to withstand fault currents without damage. Supplemental protection can be provided by adding devices such as fuses or surge protective devices, SPDs, to further limit fault currents or protect against voltage surges caused by faults. An engineering assessment involves performing a detailed analysis of the electrical system to determine the actual fault current levels at various points and to evaluate the effectiveness of the existing protective devices. This assessment can help identify potential weaknesses in the system and recommend appropriate solutions. In conclusion, the electrical inspector's concern is valid and should be addressed to ensure the safety and reliability of the electrical installation. By carefully considering the fault current availability, conductor withstand capacity, protective device characteristics, and code compliance requirements, appropriate solutions can be implemented to protect the number 12 wire and other electrical equipment from damage caused by fault currents. Consulting with a qualified electrical engineer is recommended to perform a thorough assessment and implement the most effective solutions.